Welcome to this lecture on array pattern synthesis. In the previous lecture, we have discussed that in uniform array, a designer does not have sufficient control to specify the side lobe level and the directivity or the main lobe beam width. So, that is why a more complicated thing is if we also change the individual excitation amplitudes, they are varied, or we will say that complex amplitude, that means the individual excitation amplitude and phase, if that is varied, then we will see that for better control can be exercised on the shape and width of the main beam and on the location and amplitudes of the side lobe. So, thus it will be this topic, that is why that we can, so that we can synthesize a given specified pattern that we will do. We will completely restrict ourselves here in the U plane. So, array factor we will see, we will take the FU and we will specify how to choose the excitations, individual element excitations to achieve at a different one. Now, there are various techniques, actually this is an active area of research, even now also it is evolving, because there are actually one thing we are not considering, that mutual coupling between the array elements when they are placed closely. So, that actually changes the whole game plan, because here we are saying that there is no mutual coupling, but mutual coupling changes. So, how to choose the excitation coefficient, that people are coming up with better and better methodologies, etc. We will not go into detail of all those advanced topics, but we will just see some fundamental methods by which this array synthesis can be done. Actually, we will discuss only one dimensional array, but the method that we will discuss can be easily extended to the two dimensional arrays, etc. Now, first let us look at a line array with 2n plus 1 elements. Let the excitation of each element, so elements are on the z axis, and let the excitation of each element be proportional to Cn for the nth element, that means C1, C2, etc. Here you see also we will have a C0, because we are considering 2n plus 1 element. So, there is one element at the center. So, the array factor we can write as n is equal to minus n to capital N Cn e to the power j k naught n d cos theta. Now, if we choose Cn is equal to C of minus n, then we get f becomes C0 plus n is equal to 1 to capital N 2 Cn cos n u. So, this side is, if I call it Fu, where again our, as before, u is nothing but our k naught d cos theta. So, again we assume here, actually that means here we have assumed that u naught is 0 in phase excitation. So, Cn is a complex quantity. Now, if we look at, this is nothing but a Fourier series, cosine Fourier series with n plus 1 unknown amplitude. So, if I know Fu, or if Fu is specified, I can find out this C naught and this Cn things. Note that our theta is varying from 0 to pi. So, minus k naught d to plus k naught d is the range of U that corresponds to visible space. However, so the pattern should be specified for a complete period in the U plane, that means from minus pi to plus pi. So, if the pattern is specified, we can find it approximately. So, what will be now C n value from the Fourier series knowledge, we can easily write that 1 by 2 pi minus infinity to plus infinity f, I am writing f specified or desired u cos nu du, and this is, suppose I want that the, I think in the next one it is given this is f du, that means suppose a rectangular function from minus k naught d by 2 to plus k naught d by 2. The visible space is here minus k naught d to plus k naught d for a broadside array. So, this one, so I can find C naught, that will be 1 by 2 pi, this is cos nu du because rectangular function. So, 1 here. So, this becomes 1 by n pi sin n k naught d by 2. So, for a 7 element array, you see the pattern is like this, the synthesized pattern. Now, obviously, 7 element is small, that is why rectangular is like this. If you go on adding more number of elements, you can go up to the desired pattern. So, this is one approach, it is very easy, and actually people have proved that this is a, it gives a least mean square error approximation to the desired pattern. But if you, but the problem is, you see that here you have side lobes, etc. So, if another choice is that suppose I do not want any side lobe. So, actually this method what I said, that is called Fourier series method, already you see that. Now, the next another approach is, let us see that we write the array factor as e to the power j k naught d by 2 cos theta plus e to the power minus j k naught d by 2 cos theta, because we have symmetrical those two, into 2 to the power n. Let us write like this. So, what we get is e to the power j u by 2 plus e to the power minus j u by 2 whole to the power 2 n is equal to 2 to the power 2 n cos of u by 2 whole to the power 2 n is equal to e to the power minus j n u, n is equal to 0 to 2 n c in 2 n e to the power j n u. So, actually this one, if you expand, you get this. Now, this you see the excitations here, because when I will take the array factor, this factor will go. So, this is nothing but binomial series. So, that is why this array is called binomial array. Now, we know the property that a binomial array Cn to n, this is same as C to n minus n Cn to n. So, Fu now can be written as C0 to NC0 e to the power minus j n u plus C So, you see again actually it is a sort of Fourier series, but the beauty of this is that if we choose like this, you see the pattern is like this. The visible space is same as before, because we have taken the alpha to be 0 or u0 to be 0. So, this you see there are no side lobes. So, this is the other extreme, that there are no side lobes, but what is the problem? Obviously, this beam width is much more than uniform. That is obvious, because the moment we are taking these binomial ones, so at the sides the excitation amplitude is quite less. So, actually the array length is getting reduced, because effectively the interference or the radiations from the edges, they are not contributing to the actual radiation. That is why the half power beam width is broader. So, this is an inefficient use of the available array length, etc. Now, let us come to the point that we have seen. So, if you want to, these are simple things that if you want to reduce side lobes, you can go for these. If you do not care for gain, etc., you can easily take binomial array, that is a good choice. Similarly, if you want to have an large number of elements, if you want to take, you can use the Fourier series things. If space etc. is not your constant, so you can approximate by taking Fourier series thing, and that also you can do. Now, let us come to actual our point, and that the development came mainly from Shelkunov. He actually, we were discussing this, what he said that let us do not have any negative things. Actually, that is a numbering game. So, let us number, so from one side let us start 0, so go to n. So, do not have this. So, the phase, suppose the phase now we consider u naught. So, our u naught is alpha d. So, only we have in the plus z axis the elements. This we can say without losing generality. So, array factor will be so now our element length is still n plus 1. So, n is equal to 0 to n C n e to the power j n u plus u naught. where u is equal to k naught d cos theta, u naught is alpha d. Now, let us define, actually this Shelkunov did this, he defined a complex variable z, that is e to the power j u plus u naught. So, array factor is f is equal to n is equal to 0 to n c n z to the power n. So, this z to the power n, or that means this expression is nothing but a polynomial expression of order n. That is his contribution. That so, now mathematics has richly studied these various polynomials. So, that polynomials properties will transport to the synthesis of the array patterns. Firstly, let us see this polynomial of order n has n number of zeros. This is a polynomial of degree n, if I expand capital N. So, it has n number of zeros. So, f can be written as C n z minus z 1, z minus z 2, z minus z n. And what is each factor z minus z 1? We can say, we can interpret it as the array factor for 2 element array. Thus, we say that the array factor of an n plus 1 element array is the product of the array factor of capital N number of 2 element arrays superimposed to produce nulls at the zeros of f. Also, so the total arrays pattern is the product of the patterns associated with each polynomial by itself. So, now he said, since you see this transformation, this z is this. So, z magnitude of z is equal to 1. So, for all real values of u and u naught, visible space will correspond to a portion of the unit circle extending from minus k naught d plus u naught to plus k naught d plus u naught. Now, let us see, I think, so if I have an unit circle, and now you see a designer's choice. If I have in this case the d element spacing is greater than lambda naught by 2. So, here actually if you do this, that, so this is the start of visible space, and throughout the visible space if u moves, it moves, completes one circle and then one circle once, then again come here. So, so many times it is revolving. Actually, just because it is a case of a broadside array, u naught is 0 and we have taken d is greater than lambda naught by 2. So, we can move it so many times. Now, zeros of the polynomial, that if I have more times I travel it, so I have multiple zeros at places. Now, multiple zero at a place means that it becomes more and more flat near the zeros. If you remember the Butterworth polynomial, that it has n number of zeros, any nth order Butterworth polynomial has n plus 1 zeros. So, there it becomes maximally flatter and flatter. So, if I want about the nulls, because these Z zeros are nothing but nulls of the array pattern. So, there if I want a maximally flat type of pattern, then we put more and more zeros. Actually, I draw an analogy. What happens, consider that you have a rubber band and you are holding it above some place. Now, if I at some point of the rubber band, if I pin it to the surface, okay. So, near that surface the function is bound to go to small values. Now, I pin it again another point. So, if these 2 points are nearby, then I can make the label go down. So, 0 placing is in your hand, where you will place the zeros, and if I multiple pins if I put, then it will be that maximally flat means it is not going to a side lobe up very high sharply. So, side lobes in effect will be kept below. So, this is the designer's choice, that where he will put. Actually, what designers have, that is the inter element spacing. You see this, instead if inter element spacing is lambda naught by 2, but here there is a phase shift, it is not written, it is an n-fire array. So, phase shift is minus 90 degree. You see that visible space is not even fully covered. You see this is one point, theta is equal to 0. So, visible space starts from here, visible space NCR. So, all the zeros need to be placed here. In the non-visible zone, no visible, the zeros will be placed. Okay? And let us say that I want theta at this point, u naught is this, it is minus pi by 4, d is in between 0.75 lambda naught. You see that it is starting from here going and one full circle, then up to some distance. So, because where is your theta is equal to 0, that is important, and then how much you are covering. So, here you see that no zeros are kept here. So, all the zeros you see the designer has placed in these points. So, that the second time the portion that is circling, that is seeing a twice 0. So, more flatter things. So, this type of things can be done. So, let us see it in more detail. Suppose I choose the array factor to be that I will place, let us say that all the zeros, that means sorry, I have an n plus 1 number. So, capital N number of zeros I am putting at z is equal to minus 1. What is z is equal to minus 1? Z is equal to minus 1. From here you can see that that means my, let us say for u is equal, u0 is equal to 0. So, z is equal to minus 1 means theta is equal to 0 and pi. That means at the at 0 point and pi point, theta is equal to pi point, I will put the zeros, so many zeros. And if we expand this, then we get that Butterworth thing, binomial thing. So, it becomes z n plus z n minus 1 plus n C2 z n minus 2 etc. plus NCN. So, this is actually Butterworth, and you see that is why there are no side lobes. That is why the whole thing, if I can do this, then there are no side lobes, because you think a rubber band has been put, the zeros are coming at the two ends of the visible spectrum. Actually, 0 and pi are the two ends of the visible spectrum. So, that is why it does not have any lobe. Now, consider that instead of these I square these. So, that means suppose let us say an array polynomial is like this 1 plus z square plus z cube plus z fourth, and I want double zeros at all these 0 points of this polynomial. So, I can square this and that will become that 1 plus 2z plus 3z square plus 4z cube plus 5z fifth plus 3z 6 plus 2z 7 plus z 8. So, this becomes a 9 element array with the excitation functions. You see I have triangular distribution 1:2:3:4:5:3:2:1. Now, you can see the array factor for this, that the 5 element array is the black one and the dash one is the that squaring that gives you 9 element array, where it is becoming in near the 0 more flatter. So, I can reduce the side lobes, obviously I will have to increase the thing, and this is the placement of zeros, at which point you want to put the zeros, etc. So, by this you can go on. Now, the question is, which in any synthesis problem finally is asked, that what is the optimum of this? Suppose I am specifying side lobe levels, what is the maximum directivity I can obtain, or conversely if the directivity is specified, what is the minimum side lobe level I should suffer. So, that is an optimum problem, and that problem was solved by Dolph. So, that is why it is called Dolph's array, or actually you see that for that we look into the, I recall actually I think we have seen it, you can see my NPTEL lecture on the impedance matching basic tools of microwave engineering, where we have discussed about Chebyshev polynomials. Now, Chebyshev polynomials have a very nice property. Actually, I am not again discussing Chebyshev polynomial, but we can see the properties of Chebyshev polynomial. Actually, this is various order of Chebyshev polynomial here. So, you see that it is a T n x. So, you see T1, T2, T3 x etc. all have a property that it oscillates between x is equal to -1 to +1, and after that when it is more than x is equal to 1 or less than x is equal to -1, monotonically it increases. Actually, based on this we have in the impedance matching or filter designs, we put pass bands here and stop bands here. Now, here what we will do, we will, you see that the oscillations also, so are all confined to +1 to -1. So, we will put all the side lobes in this zone, and one side will pin with, let us say this one, another side, because the main beam, certain cases in end fire etc., the main beam comes at the end. So, there I can go up. So, certain portion I will cross x is equal to 1, because if the main beam is there, then there is no problem. I am actually putting more directivity. Actually, this thing I mentioned in discussing end fire array, that sometimes in Dolph Chebyshev arrays a portion in the invisible space is gone. Actually, that comes from here. Actually, these arrays are called Dolph Chebyshev arrays. So, here I will go a certain point greater than these. Based on what? Based on my the specified side lobe level requirement, SLR requirement. So, let us see that to this, let us see a second order Chebyshev polynomial, and here you see our function is, instead of x I will write it as a plus b cos u. Please remember, because our actual function is or cos u or something we can say, but actually our u is what, that k naught d cos theta plus u naught. So, this is the form is similar here, though this u may be confusing, but let us see, a plus b cos u is equal to, if you do this, there are formulas given in the book, also in my NPTEL lecture you can see that, basic tools. That is why we call it basic tools, many times we are using it in microwave technology. So, here also you see that this second order polynomial can be written as a Fourier series in U. If we go for T3, then that becomes 4a cube plus 6ab square minus 3a. Which is also a finite Fourier series. In general, T capital Nth order Chebyshev polynomial is a finite Fourier series up to the term cos n u. And so, I can say that it can be identified, or we can say that this is the array factor for an array with 2n plus 1 elements. For a symmetrical broadside array with 2n plus 1 elements, the array factor already we have shown that it can be written like, the Fourier series time we have written this. This can be equated to the Chebyshev polynomial of degree n. The constants a and b can be chosen to make the visible range of u correspond to values of x in T n x, that range from x is equal to minus 1 up to, so we say that up to x is equal to x 1. So, that means x is equal to minus 1 to x is equal to x 1, where x 1 is greater than 1. So, people have done that, and on what we will find the a, let us say that this x 1 value. So, before that, if you solve this, you can get some design formulas are given, I am writing, but there are various cases, various assumptions. So, something like to give an idea that you can find out the these a b constants as something like this. And b is so, you see that once I can find x 1, a b can be determined. The moment a b can be determined, you can find out various things. If this d if the d becomes lambda naught by 2, then A becomes x 1 by 1 by 2, B is equal to x 1 plus 1 by 2. And how they vary? You see that in the u plane, u versus x, this is the variance, and maximum it goes to A plus B. You see it is initially increasing, going up to A plus B, then coming down again to minus 1, and this is about the k naught thing. So, theta and this, their relation is this. Now, the question is how to select x 1. So, let the side lobe level SLL be specified as R. So, we require Tn x 1 is equal to R, because it is in the, I require the main beam. So, where the main beam, this value is more than 1. So, I require it here. So, at what point? Based on the SLR specification. So, if SLR is this, then I will put it here, and hence I can say what is Tn x 1. If you look at its expansion is cos hyperbolic n gamma 1 is equal to R, and so this x 1 is cos hyperbolic gamma 1 is equal to cos 1 by n cos hyperbolic R. So, from R, n I already know the number of elements I want to put, x 1 is found, the moment x 1 is found, a b is found, then the constants a b found means you now know. So, what is the beam width, etc., you can easily say that this is the optimum design, that given a side lobe I can find what is the maximum directivity that I can obtain. In some designs the opposite, the beam width is given, that means the directivity is given. So, in that case the main beam extends from the last 0 of Tn x before x reaches the value of 1, that means last 0 is here. Suppose I am taking T1, or let us say this is T2 or T3. So, T3 is, this is the 0 of T3. So, from here up to that, let us say this point. So, the main beam extends from the last 0 of Tn x before x reaches the value of 1 up to x 1. If the beam null is placed at theta z, then the corresponding value of u you can find, and then x z you can find. So, that value x z, that will become, this is the point of 0 before the last one. So, cos pi by 2 n is equal to a plus b cos u z. So, finally, with the help of this, a becomes minus cos u z plus x z cos k naught d by cos u z minus cos k naught d. B becomes 1 plus x z by cos u z minus cos k naught d. The beam maximum to side lobe level ratio R can be found from Tn x 1 is equal to Tn a plus b is equal to R is equal to cos hyperbolic n cos hyperbolic a plus b. Since at u is equal to 0, we have x is equal to x 1 is equal to a plus b. So, we can also specify the side lobe ratio parameter R, in which case the beam width is fixed and can be found from the known value of x 1 and the value of x. So, okay, this is involved. I am not going into details of derivation, but Dolph Chebyshev array you can easily see there are good references available. Now, let us see, this is a design that in this case 20 dB side lobes are specified. So, you see that this can be obtained, this is the visible space, and you can find out that there are actually 1, 2, 3, 4. So, 5 elements are used. By that you can get 20 dB side lobes, etc. Actually, theoretically you can, with this, not only with Chebyshev, with others there is a term called super directive array in a thing. Actually, anything which is a order of factor larger than the uniform array's 13.5 dB side lobe level, that is called super directive array. So, it has been proved that you can have with this synthesis procedure, you can achieve any directivity with the a limited or given array length, but those are not practical. Actually, if you do that, you will see that they require, one thing is very high currents, excitations. Typically excitations may be in the 10 to the power 6 amperes, etc. So, very high. Another thing is they require generally that the adjacent elements, they should be oppositely phased. So, what happens due to that high, one thing is it is very difficult that if you have a very high current excitation and nearby to have a 180 degree phase opposite, and what happens ultimately there, though theoretically it is possible, but actually the loss is so high in those structures because of such high current that ohmic losses are much larger than the radiation resistance. Since we are not taking any losses into account, ohmic losses into account in this, so they show that okay, the directivity is very high, but actually the practically those antennas, the so these super directive arrays are no, but maybe in some day if some loss control mechanism is found, then that can be a promising one maybe someday, because maybe the excitation etc. that can be done provided the loss can be controlled. So, it is not that research has stopped in that direction. So, super directive arrays with the new various materials etc. they are maybe promising one day. So, array designer, antenna people should not lose sight of that, that it can be possible to design very high directivity things given a limited a thing. With that, this is an advanced topic. So, maybe the material etc., the formulas etc. are not so important, but the concept that comes, that how we can do that, how Shelkunov made that polynomial thing. So, there are various other polynomials which are also candidates, very effective candidates. Chebyshev may be one, but there are other polynomials also which has various good characteristic which can be easily ported to this framework, and then it can be explored. Thank you.